Hi, Sam Schiffman here. Welcome to my low budget series on what's in my mind. Today I'm going to be talking about why I've become convinced that agentic is not just another buzzword. It's not just the next blockchain, but I really do think that agentic is going to be the future of computing. And I'd like to talk a little bit about why. So, in order to do that, I'm going to need to go back and talk a little bit about the history of computer programming. So um, let's clean off our board and get into it. So if we go back kind of to the beginning of computer programming, right? You had very linear programs, right? You had one operation that happened after another operation, right? And these were all working on some data. Here, I can make that a little darker. As I said, this is low budget, unscripted, so bear with me. But we have one step after another, right? Eventually, we have some branching logic where we have if statements that can go this way or that way, right? And eventually we have go-to statements that let us go back a little bit. And all of this is working on data that, we're kind of very loose data types, such as just essentially memory buckets, like integers and eventually in characters and then eventually strings. You don't get very complicated data structures, maybe some arrays at some point, right? We progress on through the history of computer programming, and we start to get procedural programming, right? So in procedural programming, we have a procedure here, right? And the code can decide to call that procedure here, and code can progress and call that procedure again there. And now we have some nice code reuse. And we also start to introduce this idea that is called structs, which is data structures. We start to introduce more interesting data structures, and one of them is struct, which is a collection of data together. And data is state, right? It's the numbers and the words and the things which describe the universe, and what's going on, right? And it's holding the state, whereas the program is holding the logic, or what's going to happen, or as we'll talk about, kind of behaviors, right? Okay, so we have linear programming becomes procedural programming, which lets us reuse code. But both of these are essentially this kind of workflow approach, right? They start at some point here, they go down, they'll have some kind of branching logic, they'll have some operations, right? Another branch, which might branch again, right? So that branch goes and has some other operations, and maybe this has an operation here, but this after that wants to call that, and they start to get very, very, very complicated, right? And so building systems at scale ends up becoming pretty difficult in these kinds of languages, as those flowcharts start to get very, very complicated, right? So people were trying to think about, okay, how do we solve that problem? How do we simplify is the wrong word for it, but how do we figure out how to capture these complicated systems in computers? And people started looking at the world around them and started to say, okay, well, the world is complicated. Maybe there's some solutions that can be found out in the world, right? And they realized that one of the things that was happening was this separation between state and and behavior and action and what to do, right? They realize that, like in the real world, if I have a ball, right, that ball has a location. That location is, an X, Y, Z, right? Some location, right? If I push on the ball, right, the ball's going to roll and that's going to change its location, right? That change in location is a behavior of the ball rolling. Now, in reality, it's an interaction of a bunch of physics properties of the ball is on a surface which has some friction and it's had a force applied to it, and it's so that behavior depends on a lot of physical laws, which some complexity we'll get into in a moment. But the main thing, the point that I'm making here is that this is an object, a thing in the world that has state and behaviors that can change that state. And the argument that they made was that only through the behaviors, like being pushed on, can the state change. So if we start thinking about computer programming that way, maybe we can solve some of these more complicated problems. All right, maybe that's the trick, right? So they introduced what's called object-oriented programming, or OOP, right? So object-oriented programming comes in, and object-oriented programming says, let's combine the state, so state plus behavior, and further, let's protect the state. Only the behavior can change the state. So only behavior can change state, right? And that's all within what we call an object. I'm not going to get into the distinction of classes and abstract classes and all that sort of thing. And another element of object-oriented programming is certainly inheritance, which I'm also not going to get into here. But this key way of modeling the world is what I want us to think about, right? So this is great, right? Okay. So let's now talk about kind of a simple, relatively common problem that we do in computer programming, which is order entry, right? Okay. So we'll have a user object, right? And we'll use this notation to show that that's an object. And then we'll have an order object, right? And then, maybe we have a payment object, right? And then there's some items that are in inventory, right? Those are the things which somebody is ordering, right? Okay. We can draw this whole thing out and can get complicated. A user is going to create an order, right? And then they're going to submit that order. The order is going to go process the payment. And first it's going to make sure that the item is in stock, right? That there is an item. Then it's going to go do the payment. Then it's going to tell the fulfillment department to go get the item and send it out, right? Great. Now, if you actually looked at any of the implementations of a system like this, I suspect you wouldn't see it look like this. What you would see actually is that we would have an order managing service. Okay, we'd have an order manager service, and the order manager service would be what we would call a stateless being or stateless service, right? So we object-oriented came about, everybody said, okay, combine state and behavior. And then the first thing we did was to say, oh, but in order to build systems at scale, we need to have stateless managers. And the stateless managers then work um, on orders, which really don't end up having behaviors. They end up having just state in the end. So they just have the state in them, and the order manager works on them, which is really, in many ways, getting back to procedural language programming. Um, and there are probably a number of reasons for this, right? But I think that part of it gets back to what we want out of our computers. What we want is this sort of predictability, what I would call determinism. We want, every time I go to the computer and if I enter the order with exactly the same characteristics and the state of the warehouse is the same, I'm going to get the same result. So if the item is in stock and I enter an order for the item, every time it's in stock, I want to actually have the item, and my payment processing goes through line, I want the item to get shipped out to me, right? And that kind of determinism that we want out of computers and have wanted all along is not necessarily a bad thing, but it flies a little bit in the face of what we said originally with the whole point of object-oriented, which was to think about how we can model our world and what happens in our world in the computer in such a way that we can solve complicated problems. Because as soon as the system starts to get really complicated, it gets hard again to deal with. As soon as you start to say, okay, well, what about, all right, well, the warehouse has the item in stock, but now I have 15 warehouses all over the country, and which one is closest to the person so that I can ship it to the right person, to the right address from the closest warehouse. But then maybe there's a weather event, and that warehouse, it would actually be harder to get the item out of that warehouse because there's a storm in between the two. So it might as well come from another warehouse that's technically farther away, but because of the conditions, it's going to be faster to get it to the person. All of these things, right? All these things become more and more complicated. And it gets more and more complicated. And, we find solutions to these. Certainly Amazon has gotten very good at figuring out how to deliver the item from the right warehouse to get it to you as fast as possible. But it gets extremely complex. And you would argue that ordering an item and getting it shipped to you is probably kind of simple compared to the kinds of things that you want to do. And in one of the future talks, I'll hopefully talk a little bit about healthcare and why I think healthcare is where agentic is going to really take off because of these complexity issues, right? So our desire, our current model, our way of working in computers, which we want to be deterministic, hits a wall at a certain complexity. And what I think we really want, if you look at, say, the computer on Star Trek or Jarvis in Iron Man, right? What we really want is a computer that's able to deal with any sort of complexity, that's able to break that barrier, which we have actually set up for ourselves in asking the computer to be deterministic. So along come LLMs and other generative AI. So large language models are just one form of generative AI. You also have vision and image generative AI and so on and so forth. Multimodal, where you bring a bunch of it together. One of the things that LLMs discovered was that if they were deterministic, if they always return the same thing, they didn't work very well. So, to talk about an LLM again, right? And I'm using an LLM as a representative of any generative AI, right? So we have an LLM, right? At its heart, what it's doing is, the dog, right? And it's trying to predict what should be the next word. Now, in actual LLMs, it's the next token and all those details, right? That's great. What they found was that if it always predicts runs here, right, it ends up sounding very, very robotic, right? But if instead it predicts 5 different things, possible things to see, the dog sits, the dog runs, the dog jumps, dog eats, right? And then randomly add some randomness and picks one of these randomly, right? Then that helps it sound actually more human, right? And that got me to thinking, okay, that's interesting. So what they've introduced is some non-deterministic behavior, which has actually helped the system look more robust, look more complicated, and able to handle more complicated situations. So that seemed really interesting to me when I kind of wrapped my head around it. And what I realized was maybe what the problem, the barrier of complexity that we've hit is that we're so caught up in this idea that computers are going to be deterministic for us. If we let go of that idea, that they have to be deterministic, and we admit that they could be non-deterministic, right? Would that enable us to break that barrier of complexity and produce the systems that we really want to interact with? Which got me to thinking, and then I started looking into agents, right? So let's talk a little bit about what agentic is and what an agent is, right? An agent is, I would argue, just any piece of code that has, we're going to draw this in this way. So it has some sort of logic at its core, some sort of way of interacting with the world, and some sort of set of tools and memory. And you can do that, like that doesn't have to, it's probably not readable. So let's clean that drawing up a little bit, make it a little bit bigger and a little bit easier for you to read. So there's some logic, core at its core. There's some interface with the outside world, right? And then around the outside, there's some tools, which are things which the logic can use to interact with the outside world. And there's memory or data that the system can have access to. Okay. At its core, the logic, that logic could be completely deterministic. It could be a completely deterministic algorithm that runs and is going to do the same thing every time you run it. that still would qualify as an agent. That's why we have the term agentic. So that's where we mix. When I use the word agentic, what I'm talking about is an agent that has an LLM at its core, a large language model at its core. Now, honestly, it could be a large language model, or it could be some other, a multimodal model at its core. That generative AI at its core, right? But I'm going to use an LLM for right now, just because it's easier and simpler to talk about one form rather than. So if we put the LLM at its core, then the agent becomes non-deterministic, because the LLM might respond slightly differently. What's interesting is the LLM has inside it a memory. Actually, it's an internal memory. I'm just going to say IM for internal memory, right? So it has an internal memory inside it, which is all the things that it's been trained on, right? It's been trained on a great deal of information out there, and has a. I mean, it's not really a worldview, but it you can kind of think about it that way, right? So it has this internal memory of all the data that it's been trained on, right? Generally, in an agent, we interact with it with the prompt. Now, most people these days think of that prompt as coming from some sort of chat interface from a user, but it doesn't have to. It could come from another agent. It could come from some sensors that are out there in the world, giving it information. And then it has the set of tools it can operate, which can be all kinds of things, right? It could be APIs that it can call, right? Like a weather API, or a map API that's going to give it directions. It could have updating databases, right, as a tool that it could use. It could have talking to users as a tool, right? There's all kinds of tools that you could envision. There's searching the web, right? Is a common one that an agent sometimes has, right? So the agents can have all these tools, and then they can have access to external memory. We generally end up calling this, in the agentic world, RAG, or retrieval augmented generation, where we have, and getting into the details there is not important for this conversation, but we have some vectorized data or various different data schemes. When we take the prompt and we find out what data is most reasonably combined with that prompt to give the LLM more up-to-date data. For example, news from today, or anything that's changed since the LLM was trained, so it would not be in its internal memory, right? All of this together gives us a unit that is able to actually be adaptive, right? It's non-deterministic in nature, right? So if it gets input that it didn't get before, it's not just going to not work. It will do something. It may not do exactly what we want it to do, but it will do something, right? So that opens up this possibility with a network of agentic agents, that opens up the possibility to build a system that is non-deterministic, but also has the ability to, on the fly, deal with complicated situations. So that situation that I was talking about before, where we had an order entry system that just exploded in complexity because we had multiple warehouses because of weather conditions, so on and so forth. If we built a network of agents that understood all of that, right? So in what we call their system prompts, they had enough information to understand kind of the parameters of what they're supposed to do. They can actually non-deterministically figure out how to respond to different inputs. And I think doing that with a deterministic system, with a with the traditional approaches to programming object-oriented systems would be just gargantuanly impossible. You couldn't code all those possibilities. But the interesting thing is that an LLM could potentially deal with all those different possibilities. So I think that the reason why agentic is going to be the future is because it opens up the door to non-deterministic programming, which I think is what we need to break through that wall of complexity and start solving problems and producing systems that look a whole lot more like the computer from Star Trek or Jarvis on Iron Man, and are actually the kinds of things that we would want to interact with, that know how to just solve our problems, where we're not opening apps to do things. We're just asking the computer, hey, do this, and it figures out how to do this. But even more than that, the computer is constantly understanding its world, getting input not just from people, but also from sensors and other things, which are its senses, its eyes and ears, and making logical operations based on that. Which still involve humans in the loop for a long time. Believe me, I'm not saying that we just let these agents run amok without people being involved. But we are able to build much more complicated systems that can solve much more complicated problems in ways that we really want them to. So that's why I think that agentic is not just like blockchain, which was just about being assured of state, right? It's not just like many of the other buzzwords that have come up in computing. It is truly fundamentally making it possible to get to that next level, to go from linear programming to procedural programming to object-oriented programming to truly actually object-oriented programming, and not just what I think we do today, which is I would call a pseudo object-oriented programming. So thank you very much for listening. If you've made it this far, would appreciate a like or a subscribe. I would love also a comment. I always want to continue this conversation. And if people enjoy these, I will make more of them. I'd like to talk a little bit about what the frameworks are that are necessary to make this possible, because it's not just one agent, it's multiple agents being able to interact with each other. And then also talk a little bit about why this will be applicable in healthcare, and other thoughts that are in my head going forward. Thank you. Have a great rest of your day.